Next, we want to turn our attention to properties of different substances and how intermolecular forces relate to those. We're going to start by talking about liquids in particular and what different properties liquids experience because of the types of intermolecular forces they have. That is, if there are more intermolecular forces, can we say something special about this type of substance compared to something else? So the properties and also the structure of the liquids themselves relate to their intermolecular forces. One of the first things is surface tension. So here we have a picture of a water droplet in a zero gravity environment, probably in space here, and notice it takes this spherical shape, which we don't really see on Earth all that often. This spherical shape is a result of water surface tension. Surface tension is the tendency of a liquid to minimize its surface area. Remember, those water molecules are really attracted to each other. And so the only way they can all get the maximum amount of touchy-feeliness of attraction to all the other molecules that are present is by creating this type of surface tension. And so a lot of liquids display surface tension, and it's a result of the attraction of one molecule with another molecule, so intermolecular forces. So surface tension itself, notice here's a paperclip floating on top of the surface of the water. That means the paperclip doesn't have enough force to break apart the attraction those water molecules have for each other and fall down into the liquid. This is also how bugs, walk on water and that kind of thing. So there are cohesive forces on the surface and the molecules that make up the surface, and so therefore they have a strong attraction for one another, and they keep the liquid connected as much as possible, unless something has enough force to overcome that. So it's sort of like this paperclip is floating on the surface of the water, but we know it's not really floating, it's just not capable of breaking through to get down into the liquid. So here are some molecules on the surface and a picture of sort of what that looks like. Notice they're interacting with their neighbors, but there's no molecules on top to interact with. But further down into the substance, like this one here on the interior, there are lots of places it can interact, and so this creates surface tension in the substance itself. And that means since there are fewer neighbors for that one on the surface to interact with, it's going to be less stable, and it's going to have a higher potential energy. And that means the amount of energy required to break one on the surface away from the liquid itself is going to actually be smaller than it will be down in the liquid. And it's going to relate to the amount of intermolecular forces. So the surface tension of water is about 72.8 millijoules per square meter at room temperature. And notice we're going to compare that to the surface tension of benzene here, C6H6, which is 28 millijoules per square meter. And so how can you account for that difference in surface tension? And the answer is intermolecular forces. Notice C6H6 doesn't have hydrogen bonding, doesn't have dipole-dipole forces, and so water we expect to have a lot higher of a surface tension in that case. Now there are other factors that play a role which make it a little bit harder to understand at times, but surface tension relates very strongly to intermolecular forces. So what factors mean that you have a higher surface tension than otherwise? Well, obviously if you have more intermolecular forces, you'll have higher surface tension. And if you change the temperature, you're going to change the amount of surface tension that's present. So if you increase the temperature, if it gets warmer and warmer and warmer, remember you're giving more kinetic energy to those molecules, which means they're able to move faster and vibrate more and rotate more, and therefore having more kinetic energy, it's going to be easier for them to overcome the attraction the molecules have for one another because they're able to move around a lot more. So increased molecular motion through increased temperature because of an increased kinetic energy means it's easier then for the liquid to overcome its attractive forces at the surface. And so if you have a higher temperature, typically you're going to have a smaller or lower surface tension. And notice here as the temperature is increasing, the surface tension is going down, 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 down. This is for water, of course. And so higher temperature leads to a lower surface tension. Viscosity is another property that relates to intermolecular forces. The more intermolecular forces, the more viscous a substance is. Remember, viscosity is just the resistance of a liquid to flowing? Does it desire to flow, or does it resist flowing? And often we just think about viscosity as being how sticky something is, because it doesn't want to flow very much. Okay, it's measured in units of poise, or more often in centipoise. And notice each time I'm increasing the chain here for these hydrocarbons, and you can see the formula, the chain gets longer and longer and longer. As that chain gets longer and longer, the molar mass goes up and the surface area goes up, so the dispersion force is going up. So increased dispersion force as we make that chain longer. Therefore, we're predicting increased viscosity as we move along with the longer and longer chain, which is exactly what we see experimentally. Now, what affects the viscosity? Obviously, it's going to relate to the intermolecular forces. More intermolecular forces means larger viscosity, because those molecules don't want to flow past one another out your honey jar onto your biscuit, right? What factors can affect it? Well, we can change the temperature as well. Often for one particular substance, if we want to change its viscosity, we don't have the option of just getting a different substance. But what we can do is affect the temperature itself. So increasing the temperature will play a big role in how viscous something is. Imagine you get the honey out, or you get the syrup out, or whatever the case may be. If you want it to be less viscous or to flow more easily, what do? You warm it up. You put it in the microwave. You take it out. It pours a lot easier. You've changed the viscosity by altering the temperature. As you increase the temperature, you give more kinetic energy to the molecules. Those molecules are able to overcome the interactions they have with each other, and therefore they can flow past one another a lot more easily. So you've adjusted the viscosity by adjusting the temperature, or the kinetic energy of those molecules, right? Higher kinetic energy means greater temperature. So kind of use those words interchangeably, although they're not exactly the same thing. Okay, if we could increase the dispersion force, that would alter the viscosity as well. If we could increase any of the intermolecular forces, we could affect how the viscosity works. Okay, here again, temperature is going up and the viscosity is going down. Notice it's not linear, and we've got kind of a curve here. And this is the viscosity of water, which we normally think of as not a very viscous fluid. And indeed, notice as the temperature goes up, the viscosity goes down. Okay? So as the temperature goes up, the viscosity goes down. Inversely related. As intermolecular forces increase, the viscosity would increase. We're going to think about how all these things are related. Capillary action is another result of intermolecular forces. This is essentially when a liquid seems to flow up a small tube against gravity on its own, seemingly. So you take a really thin, narrow tube and you put it in a liquid. The liquid will rise up in the tube. Now, why does that happen? We have two forces working in conjunction. One is cohesive forces and one are adhesive forces. Now, the cohesive forces hold the liquid molecules together. They're sort of like co-workers. Two liquid molecules wanting to be together. That's the cohesive forces, and that's because of intermolecular forces, right? And then we have these adhesive forces. These are the forces between the liquid itself and between the tube's surface. So we've got a tube, and we're going to put a liquid in the middle. So here's the wall of the tube, and here's the liquid. That liquid is attracted to the molecules in the tube as well, and so it can move up by being attracted to the inside of the glass, essentially. So capillary action happens because the liquid molecules are attracted to the glass through this adhesive force. And that means naturally the liquid's going to rise up inside the tube on its own, as long as the adhesive force is stronger than the cohesive force, ultimately. So we get this capillary action. And it turns out the narrower the tube diameter, the higher the liquid will rise up the tube, because more liquid can be in contact with the glass when the tube is extremely narrow. And if you look real closely at some of these, you'll notice the meniscus. And you may have made this observation in the lab when you're looking at a cuvette or a burette when you're doing a titration. Anytime you're making a measurement like in a graduated cylinder, you'll notice this meniscus of the liquid in the tube. Notice the meniscus of the mercury in the tube here goes the opposite way. Now, of course, when you're making measurements of volume and all that sort of thing, you want to measure at the bottom of the meniscus. And Why is there meniscus in the first place? Well, it relates to the cohesive forces the liquid has, and it relates to the adhesive forces that are there. Notice in the case of the mercury, the meniscus is convex because the mercury atoms want to stick to each other more than they want to stick to the glass. And in the case of the water solution, the red one here, the adhesive forces are strong because the water wants to move up the glass itself instead of being stuck to its own molecules. This is all part of what we call the molecular dance. Remember, molecules are constantly in motion, and they have some average kinetic energy, which is directly related to their temperature. And some molecules in general can have more kinetic energy than the average, and some will have less, but there is an average that sort of dictates how fast the molecules can move. If you give it a higher temperature, they'll have a greater kinetic energy on average, and so they'll be moving faster. This can lead to phase changes, which is what we want to discuss next. Okay, so we're moving into section 5 here, vaporization. So vaporization is really the process of vaporizing a liquid in this case, or a solid really, but in this case we're turning from the liquid phase to the vapor phase, or from the liquid phase to the gas phase. And why is it that some molecules can evaporate, or some substances do it really easily, and others take a long time? You can think of acetone or fingernail polish remover. It evaporates really fast. It evaporates so fast when you spill it on your skin feels cold. And if you spill water on your skin, it takes water a lot longer to dry on its own. That's because they have different rates of vaporization. And so this relates to a few things, including intermolecular forces. It also relates to how much of the liquid is exposed to the atmosphere. So the larger the surface area of the liquid, the faster the rate of evaporation can happen, because there are more surface molecules, so to speak, compared to ones that are down in the liquid itself. This means those surface molecules can more easily become vapor. Remember, they don't have as many attractions because there's no molecules above of that liquid. And so they can more easily escape into the vapor phase from the liquid itself. They can evaporate, or they can vaporize. So remember this graph we looked at when we were looking at gases in the gas chapter. And this is the distribution of thermal energy. So notice at higher temperatures, more molecules on average, since we're talking about the fraction of molecules here, more molecules on average have the amount of energy needed to escape the liquid surface and turn into vapor. And notice at the lower temperature, there's not as many molecules that are capable of doing that. They can't. Not as many molecules can gain the extra energy they need to escape the surface of the liquid and turn into the vapor phase. So overall, what we're seeing is the higher the thermal energy, or the higher the temperature, the more easily molecules can obtain the escape energy and evaporate. The higher the temperature, the faster the rate of evaporation. That's why you might take something in the lab, like a beaker, and put it into the oven, so that way you can make sure it dries out all the way and faster and all the water is gone. You increase the temperature, you've increased the amount of energy that the liquid has, and therefore its ability to escape into the vapor phase. Thinking about it the other way, we have the process of condensation, turning from the vapor, losing energy, turning back into the liquid phase. And so anytime molecules lose enough energy through molecular collisions, colliding with other molecules or a container wall or that kind of thing, they can lose energy, and eventually they will lose so much energy they're attracted to the liquid again, and they come down and they stick to the liquid. So they've condensed from the vapor phase down into the liquid phase based upon changing temperature and changing amounts of energy. Ultimately, they stick back together, form droplets of liquid, and form droplets on surrounding surfaces and that sort of thing. Imagine taking a soda that's cold and putting it out in the humid environment, and essentially very quickly it gets condensation droplets all on it because it's so cold. As the water vapor in the atmosphere around collides with that cold can, it's able to suck a lot of the temperature, a lot of the kinetic energy out of the water vapor, and therefore the water vapor cannot overcome the attraction it has with other water vapor molecules nearby, causing them to stick together and turn into liquid droplets. This is the process of condensation. So you have both of these processes happening at once: evaporization or evaporation or vaporization and condensation. So evaporation and condensation are essentially the same process. One is escaping into the vapor and one is coming back down into the liquid. They're just opposite of each other. Sort of depends on whether you're leaving the liquid or whether you're coming back into the liquid. Why and how much energy does it take to do these processes? Remember, each of these are going to relate to the amount of intermolecular forces that are present. And we're going to say on average that any liquid that's exposed to the atmosphere around it in an open container is undergoing vaporization processes and condensation processes such that they reach an equilibrium often, especially if it's a closed container. The rates of evaporization and condensation will be equal to one another, and the liquid will never slowly disappear all the way. Whereas if you left a beaker open with liquid on the bench top in the lab, you could come back 2 weeks later and it might be dry because all of the liquid has evaporated into the surrounding atmosphere. Whereas if you put a lid on it or some parafilm on it or whatever, it won't do that. It'll form an equilibrium between evaporation and condensation back and forth. So how does intermolecular forces affect this equilibrium that's established? Remember, we have to overcome those attractive forces in order to vaporize, and when kinetic energy is lost out of the molecules in the vapor phase, they feel those attractive forces a lot more and they want to condense back together. So the weaker the attractive force, or the weaker the intermolecular force, the faster the rate of evaporation. The weaker the attractive force, the faster the rate of evaporation. So that means high intermolecular force means low evaporation rate. Actually, there are some substances that are liquid that have such a high intermolecular force that they don't evaporate. It's kind of interesting. A whole class of liquids called ionic liquids. Some of them evaporate, but many of them don't. This is why we say that liquids are volatile substances. Some are more volatile than others, and the volatility relates to how easily a liquid can evaporate, right? So if it's a really highly volatile liquid, that means it's going to evaporate very, very fast. There are some substances in the lab, like dichloromethane that we talked about earlier. When you pour it out into a beaker and you set it in a fume hood, it's going to evaporate within 5 minutes, whereas water wouldn't evaporate quite so fast. It all relates to how volatile the liquid is. Water being pretty non-volatile, well, more volatile than something like motor oil, but non-volatile compared to something like acetone or dichloromethane. And it all relates back to the intermolecular forces that are felt. Okay? These intermolecular forces... actually, what I want to say is let's talk about the energetics and the energy it takes to do these processes in the next video. So I'll see you then.